Hello everyone, welcome to a new lecture of our course on heterogeneous systems. Today we talk about a new parallel pattern, merge. This is one more of the parallel patterns that we have covered in this course. We started with the reduction operation that reduces a set of values to a single value. It has properties as associativity, commutativity, and an identity value. And we studied how to map to the GPU warps without divergence in order to maximize the SIMD utilization of the warps. We also talk about the histogram, a way of reducing the dimensionality of a large data set. In the histograms, what we do is counting the number of occurrences of each different values in the input, and we do that by incrementing some counters called bins. Because we may have in parallel implementations more than 2 threads updating the same bin, we need to use atomic operations to prevent data races. But the problem with atomic operations is that they serialize the execution. So we studied a way of alleviating the overhead of this serialization. That is called privatization. We compute subhistograms and then we reduce them. We also talk about the convolution. In the convolution, as you might remember, we have a filter or a mask that we place on each element of the input, and we calculate the weighted sum. Convolutions are very important these days in machine learning and artificial intelligence, specifically in convolutional neural networks. We talk about the 1D convolution that is used in audio processing, and as you can see in this example, M, which is the mask or the filter, is applied on top of each of the elements of N, computing some partial products and performing a reduction and obtaining the final value, 57 in this case, of the output array P. One way of implementing convolutions in a fast way and in an efficient way for GPUs is converting them into matrix multiplications. In the matrix, so what we need to do is unrolling the input feature maps and also the convolution filters in order to obtain 2 matrices that are multiplied, and this way we obtain the output features. Matrix multiplication is very much efficient on GPUs because there are very useful optimizations and efficient optimizations such as this joint register and shared memory tiling that we explain in one lecture. After that, we talk about prefix sum, which is an operation that takes an input and an associative operator and computes the output recursively. Remember that there is exclusive scan and inclusive scan, and we discuss how to implement a hierarchical scan. First of all, we calculate the scan inside a block, then we scan the arrays of partial sums, and finally we update with certain offsets per block is the array of per block inclusive scan. This is one of the implementations, the scan add implementation. We also talk about the reduce scan, which might be more efficient for large arrays. We also talk about the sparse matrices. Remember that a sparse matrix is one matrix where most of the elements are 0. And we talk about several matrix compression formats, for example, CSR, which is one of the most commonly used. Related to sparse matrices, we also talk about graph traversal or graph search, and we use breadth first search as an example. For breadth first search, we studied ways of implementing it efficiently using a top-down approach for implementing BFS, and we talk about this hierarchical kernel arrangement where we are going to use different kernels. In particular, we talk about 2 different kernels depending on what's the size of the frontier that we create after each iteration of after each iteration of the BFS algorithm. Now we are going to talk about merge. A merge is an important operation that takes 2 sorted lists as inputs and generates 1 combined sorted list. There is an ordered relation, for example, less than or equal to, and it might be stable, meaning that it maintains relative order of elements with the same value or key. And also there might be a preference. For example, elements A go before elements of the list B in case that they have the same value. Merge is an important building block, for example, for sorting algorithms, and it's also used in the reducer step of MapReduce. The dynamic nature of the data accesses makes it challenging to exploit locality for efficient access, memory access, as we are going to see. We are going to start with an example, merging two sorted lists into one, and we assume that there is an order relation, which is less than or equal to in the sorted lists and in the merge list. The sorted lists are A and B. The output merge list will be C. We are going to focus on stable sort, and whenever A and B, the elements of A and B have the same value, the element of A goes first. So, for example, if these two are the same, the element of A, that 7 of A will go first, or these two, the element of A will go first. So the way that we create the merge array is by going one by one over the elements of the two arrays, comparing them, and placing them in the corresponding location in the output array. After D7, the next element, the next small element is D7 that we place there, then 8, 9, and 10, and then these last three elements of array B. How to do this sequentially? Sequential merge is pretty simple. It basically consists of comparing the elements of A and B, as we can see here, and based on that, we decide whether we write the element of A or we write the element of B to the output array C. So we compare 1 and 7, and we see that 1 is smaller, so we write it in the output. Now we compare 7 and 7. They are the same, but because here we have a preference, we place first elements of A, we place this element 7 from A into the output array C. Now we compare this 8 and 7, the first element 7 from array B. Now this 7 is smaller, so we place it there, and so on and so forth. Now the 8, now 9 and 10, and finally the last three elements of array B, because there are no more elements of array C. So that's basically the way of doing the sequential merge. Observe that the complexity of the sequential algorithm is O m plus n, being m and n the number of elements in A and B respectively. Now, how to parallelize this? We opt for a gather parallelization, where what we are going to do is partitioning the output list equally among threads, and each thread collects the input elements from for its section of the output. For example, thread 0 is going to be assigned this part of the output, this part goes to thread 1, and this part goes to thread 2. So now thread 0 will have to fetch these two elements on A and this element of B, and place them in its corresponding partition of the output array C. Thread 1 will proceed similarly, and thread 2 will proceed similarly as well. So the range of input elements to be used by each thread is a function of the input elements, and this makes pretty challenging to find where exactly each thread has to access in array A and array B. But there is one interesting observation here, is that for any k such that k is an index of array C, we can find I and j such that k is equal to I plus j, and being I the index for array A, and j the index for array B. So if this k 0 is equal 3, we can find this I0 equal 2 and this J0 equal 1. 2 plus 1 equals 3, and these I0 and J0 are defining the range of arrays A and B that thread 0 needs to access to obtain the corresponding partition of the output array. And that's the same for the other threads as well. For example, K1 is equal 6, and we can find this I1 equal 5 and this J1 equal 1. And same for thread 2, K2 equal 9, I2 is equal 5, and J2 is equal 4. So for an element CK, K is referred to as its rank, and I and J are referred to as its coranks. So now the point is to find what are the coranks for each thread. That's the first thing that we are going to have to do in a parallel implementation. And after we know the all ranks for each specific thread, we can do a sequential merge or each thread will do the sequential merge for its own section. So how to calculate the core ranks? The key of calculating the core ranks is basically taking into account that K, which is the rank, is equal to I plus J, which are the core ranks for each individual thread, and also the observation that A of I minus 1 is less or equal than Vj, and V of J minus 1 is less than A of I. And that's what we can see here, right? So if we look at, so if I0 is equal to A of I minus 1 is equal 7, and this 7 is less or equal to this 7 here, which is J0 is equal to 1, so V1 is 10, so A of I minus 1 is less or equal than Vj, and same in the other direction. If we look at Vj minus 1, Vj minus 1 is this 7, which is smaller, is less than this 8, which is A of I, A of 2. So finding the correct values for different threads is not balanced. That's indeed an issue because the search range for the core rank of the different threads is not the same, right? So for example, thread 0 only needs to check these two elements here and this element here, while thread 1 will have to check all these elements of array A and this element of array B, and is the same for array C. The way of alleviating this cost and reducing the computational complexity from O(n) to O log n is to use a binary search in order to find I and J, and in order to find the core rank values. For the detailed implementation of the binary search for the core rank function, I'm going to refer you to the longer version of this lecture where we explain the entire core rank function. But now let's start talking, assuming that we already know how to obtain the core ranks. Let's go with the basic parallel merge, in which each thread is in charge of a continuous section of the output. So after each thread knows what's the actual partition of the output array, and in this case for thread 1, for example, it starts in k core equal 3 and it finishes in k next equal 6. The first thing that we will do for this thread is calculating the core rank values for these k core and this k next, and those are going to be called I core, I next, J core, and J next, and they define the ranges, the parts of arrays A and B that are going to be accessed by each thread, in this case, thread 1. And this is how the basic parallel merge looks like. First thing that we have is defining what's the start index of the output section and the end index of the output section. And by using them, and after knowing them, we can compute the core rank, I core, and I next. And after that, because we know that k is equal to I plus j, we obtain the corresponding j core and j next, and next we can perform the merge sequential operation. The problem with this basic parallel merge is that we have uncoalesced memory accesses. Why is that? Because thread 0 will start accessing here, while thread 1 will start accessing here, or thread 2 will be accessing here, while thread 0 is accessing here. So there are uncoalesced accesses, and the one way of alleviating these is using a tile merge kernel. basically we are going to do the merge operation in shared memory. So imagine that we have the two arrays A, B, and the output array C, and we also reserve some space in shared memory. Each individual thread block is going to do that. So first of all, we partition the output array equally, and we give different partitions, we assign different partitions to different thread blocks. And then next thing we'll have to do is find in the core ranks for each of the limits of block 0, block 1, block 2, etc. So next thing that we will do is, or threads in the same thread block will do, is collaboratively load one tile of A from the global memory to the shared memory, one tile of B from the global memory to the shared memory, and is the same for the other thread blocks. This would be for thread block 1, and this is for thread block 2. And the next thing to do is, now that we have the tiles in shared memory, we start merging them. So these two blue fractions or sections of A of S and B of S are going to be merged and placed in the output array. And same for block B, block 1, and same for block 2. So basically, we are assigning one output section to each thread block because in thread blocks, we normally have a few hundreds of threads, multiple of 32. Typically, as you know, in each section, we should have at least a few thousand elements. There is going to be a leader thread in each thread block that is going to perform the binary or NRE search to identify the input sections to find the core ranks of the corresponding thread block. And then each thread block is going to iteratively generate its output section. So in each iteration, threads of the block will go to global memory, will fetch one tile of A, one tile of B, and we place it in the global memory. We expect that each of these tiles are going to have at least a few hundred of elements because that's normally the number of threads that we have in the thread block, and they go together to the global memory and bring the entire tile to the shared memory. And then we are going to divide the output sections and assign them to the threads. And for each thread to have enough computation, we will assign at least 10 or more elements to each thread. And then all threads perform the parallel merge on input and output tiles. So, as I said, first thing to do is computing what are these core rank values so that we can identify what are the input subarrays for block 0, input subarrays for block 1, block 2, and so on. So, in the tile merge kernel, first thing to do will be to compute the core rank values for each individual thread block. Observe that there is a starting point of the current block and a starting and an ending, so a starting point for the next block, the C core and C next, and by using them, the leader thread 0, is going to execute the core rank functions in order to obtain the core rank values of C core and C next, that in this case are A core, A next, B core, and B next. Next thing to do is to load the tiles. So all threads of the thread block 0 will have to go to global memory, fetch the elements of this tile and bring them to the shared memory. Same for array B and same for the other thread blocks. So how do we load these tiles? We will have these threads of each thread block collaborating into loading one tile of a certain size from the global memory from this array A to the shared memory, this array A of S. Note that here we are using as indices the A core, which is where the core rank, so that's the core rank for array A, and this is where the specific section assigned to this thread block starts. And then we also have this A consume that it's going to, after the successive iterations, is going to account for the part of the input A and the input B that has already been consumed. So this is for array A and this is for array B. After that, we will synchronize, and now we have the tiles in shared memory. What do we do next is generating the output tiles, and that means we start consuming elements of the tiles in shared memory and start writing them into the output. And we do that for all the different thread blocks. And after we have done that, there is some part of the input subarray that we have already consumed. So for example, for block 2, this would be the value of A consumed, and this would be the value of B consumed. So in order to generate the output tile, we're going to have all threads working together. And so what we do is that the chunk of the output C that was assigned to thread block 0 to thread block 1 now is going to be equally partitioned across the threads that we have in this thread, in the same thread block. That's why now each thread is going to have its own CCur and CNext. And based on them, each thread can compute the corresponding core ranks. After that, each thread can go to the specific part of the tile of A, the specific part of the tile of B, and perform the sequential merge. And after that, we update these A consumed and B consumed in order to account for the part of the input subarrays that has already been used, has already been consumed and written to the output. There is one potential minor optimization that we could do here is generating the output in shared memory first in order to improve, reduce the latency of writing the output elements, and also writing and also improving the coalescing where writing to the output array. So now in iteration 1, we are going to continue again loading tiles. We will have to load starting from the point that we already consumed. So these are the new entire tiles that we copy to the corresponding place in shared memory. And after that, we can continue with the merging operation. The tile merge kernel has pros and cons. The pros are, first of all, that we have coalesced loads of the input elements. There is a reduced global memory traffic for the core rank functions. The thread level core rank functions are done in shared memory, as we have seen. There are coalesced stores if the output tiles are generated in shared memory, as we just mentioned. However, there are also cons, and the biggest problem here is that only half of the elements loaded into shared memory are used in the worst case. And in the next iteration, we will keep loading elements. We will keep loading the entire tile. So basically, we are wasting those elements that we loaded into shared memory, but we didn't consume in that specific iteration. In order to deal with this, we can apply one additional optimization technique that is called circular buffering. We explain this optimization technique in the longer version of this lecture. There you can find a link to the longer version of this lecture, and I hope that you will find it interesting. And you can also find this lecture in the book Programming Massively Parallel Processors in chapter 12. So I hope that you found this lecture interesting, and I also hope to see you in the next lecture of our course on heterogeneous systems. Thank you very much for your attention.